Okay. If you have question, just speak. Okay. So this is the Git page that that you have the link in the slide that contains the instruction for the setup and the link to the tutorials. And the first, maybe I can show you how to get from here to the tutorial. It's quite easy. It's you see that they are divided by days because they refer to this workshop that we had, and we will discuss the tutorials of the first day. To have the Google Colab link is enough to click here and you get directly in this. I already have the page open. So as I don't know much you are expert of Google Colab, but I understood that basically the Python version that is run in Google Colab is Python 3, and then we have each time to install the specific packages we want to use. So, for example, in this case, we have to uncomment this line and install the Ghost package. The first time you run this, you will have this warning that I have, but before this warning, you will get a request for login. So you have to log in with the Google account I already have memorized in my browser. And then when you run it, where you have this warning that so the language of my laptop is Italian. But basically what it says that this code, it comes from GitHub, so please have a look at the code before executing, and I say run anyway. So the first...
Sorry to interject there. I just
yes.
have a question from the Discord. Is it possible yes. We can post the URLs for the participants?
Where?
You can just pop them into the Zoom channel and I will propagate them into Discord.
Okay.
Possible, thank you.
Okay, I hope I copied the correct one. Is it, can someone check that I copied the correct link? Because there was I don't know if should be the correct one, otherwise, just a moment, I copy the one I had in the slide, that should be. Okay, where is it? Oh. Okay, this one should be the correct one. The other had some pointer to the page. Okay, so when you run this, for example, in my case, I ran a few times, so maybe it memorized some old version of this thing and they give you some warning. In this case, it's enough to run it twice. And then, okay, after installing, we check that the version is correct. So, okay, so and this is just the basics. So maybe I should just pause for a moment in case someone has a problem with the starting. Is, are you, okay, no one is complaining, so I go on. So once you execute the first part, now the tutorial starts. So we wrote to this, I wrote this tutorial, but the group we brought together all the tutorial with the idea that this should be run like independently. So now I will show you a bit, but the idea is that you can also just read it and get what you need. So the first cell basically use this method find dataset to check, for example, all the available catalogs. So find dataset works with, you have to define a type, otherwise you get all the dataset. And for dataset, we mean all the run, all the event, everything. So if you select catalog, you will have the list of catalogs. And this is exactly basically, if you remember the content of the page that I showed when you query the different releases we have. So, and you can see that we have GWTCY, it means the gravitational wave transient coalescence, I think. And -1 is the first catalog, and then it was decided to apply different threshold and distinguish the event in confident and marginal detection. So that's why you have two first catalog. And then there is the second catalog, initial LIGO and Virgo detection that were, so event, the first three events of O1, basically. Then O1 and O2 preliminary, so O1, the reanalysis of O1 plus other event of O2 that were published before the catalog, some event of O3 that were published again before the catalog. Okay, then another way to use this find dataset is to look for the events, for example, and you can, for example, decide to check all the events of one catalog, and in this case, you get this list, for example, and as you can see, each event is labeled with a name, and then you have some V that is the version of the event. But the code should be wrote in such a way that it shows you for each event the last version when you query in this way. Okay, then you can also look for all the dataset of type run. So the long data release that are, so this is a specific case of some background around one event. Then O1, then when we release then at some point the nomenclature changed, because when we started with the 1, the round name was simply 1, and the first release was done at 4 kHz. Then we realized that we needed also 16 kHz done, so we added underscore 16 kHz, and then starting from there, we decided to have always a coherent name with the name of the run. So, for example, O2 underscore the sampling rate underscore the release number. So for O2, you have so these two run, and O3A, which is the first part of O3, you have also the same nomenclature, and S5 and S6 were previous run before O1 that had lower sensitivity. In fact, there were no detection in S5 and S6. Okay, this cell show another example that not only when you can query for event and a catalog, but you can specify if you want to know which the event was in a particular detector, and if you, for example, want to refer only to a specific GPS interval. For each event, you can get its GPS time in this way. And in a similar way, you can have the start and the stop for each run. And this is an example in which you use basically the same command we saw here, but instead of writing the start and stop, you check which was the start and stop of O1 and use it here, so you get only the 3 event of O1. Then this package GWOSC allows you also to get directly the URL for one event. For example, in this case, you get various, you see there are many URL because you get the data at 4 kilohertz and the duration 32 seconds, then again 4 kilohertz but duration 40,000, and the same for 16 kilohertz at some point. Yes. And there are also different versions of the event, probably. Yes. Okay. For example, if you want to specify only 32 seconds, you get just this. Okay, so now that we have had a look together at all the tutorial, there are some exercises, and Google Colab can be edited, so you can maybe have a look for yourself and play a bit. So let's see, we can wait like 5 minutes so that you can have a look for yourself, and if you have questions in the meanwhile, let me know. So
I presume everybody is happily running the cells. So yeah, let's see if there's any questions, please do raise them.
Yes. So okay. So it's, what time is it? Yes, I will wait 5 minutes, and I will start with the next tutorial. So I posted in the meanwhile the link for the second tutorial, and so I think I can go on with the second tutorial unless there are objections, but everyone seems very quiet. So let's go to the second one. No, no, wait, what I did? I shared the correct screen? Yes. Okay. So,
sorry, I will,
yes?
I will post that link into Discord for everybody as well.
Okay, thanks. So in the first tutorial, we saw this package that is called GWOSC, that is mainly to get, so as you have seen, to get the name of the event, name of the run, URL, get information about the data. And then in terms of, for plotting mainly, we use a package that is called GWPy, that is very well documented. And again, if you're running on Google Colab, the first thing to do is install GWPy and give the authorization to do that. You may have this runtime error because the version of the Conda environment, when you run locally this notebook, is Iguin Pi 3.8 if you have installed Conda, and instead here the Python version is called Python 3, so that's why the Conda give you the warning. So we have just installed the GWPy and checked the version. So in GWPy, again, there is a bit of syntax to learn, and we will use this method fetch open data to get the data. But first, we have to know which data we want. So we have to get the GPS time we need. And for example, let's say we want to analyze GW190412. With the command we learned earlier, we get the GPS. And let's say we want to have a segment 5 seconds before and after this merger time. And these are, okay, the detector you already know. This command allows you to get the data from the detector L1, the segment that was defined here, and verbose equal true is to get higher level of verbosity. And so this L data now is our strain. Then we will play with it. There is, if you check the text of the tutorial here, there is a bit of note about this fetch open data in terms of which file you want to have, if it want to have the file of the event, the file of the run, and so on. And then to plot the content of the strain, this L data that we just downloaded, we use this method L data dot plot that does this. And I guess there was an AstroPy update recently, so today I get this warning that was not there yesterday, but okay. So this is a typical plot of the strain that, okay, you can see by eye that you can see nothing. It's dominated by the background, basically. And what usually the typical thing that you do with with gravitational wave data is that you check not only the temporal component of the data, the temporal behavior of the data, but also the content of the data in terms of Fourier transform. So because you want to know the frequency, what happened in terms of the frequency domain also. So this is a typical, just a plot of the FFT of the data that should look like more or less our sensitivity plot, but it's not exactly like that, because you need a bit of you need to take into account the discontinuities in when you do this FFT. So you have to apply a window. Usually we use this window, and if in this you do a bit of you check, you modify this with the window, you see that now it's nicer. Then usually we don't we basically throw away everything that is below 10 Hertz, because it's basically all background. And in any case, so this is if you use standard SciPy plot, usually GWPy allow you to plot directly the amplitude spectral density. So as you can see, it's very similar, just it's a bit different than the method that is used to average. And then you can make it a bit nicer if you select a specific interval of strain and frequency. This is usually the range important. And as you can see, this is the typical sensitivity of the detector. And this line here, a specific peak that are due to some spike that are due to specific things. So, for example, the main or some harmonic related to some characteristics of the interferometer. So there are, we call them line, they are there, and we know they are there, but when you integrate over a longer period, usually if in the standard in spiral analysis is not so important. Okay, so this line here again show how to get to do the same plot, but with a bit more data. So it will be a bit nicer because we have averaged a bit better the behavior over a longer time period. And we can do the same. So this is Livingston. We can do the same for Hanford and Virgo. And this, this will take a while to run because it has to download the data for the two detectors and then plot them together. So you see now the three sensitivity curve in, I think this was O2, yes, in O2, so in the second observing run, more or less around the time of G of the event we were looking at, that was GW 190412, so the event of the 12th of April of 2019. Okay. So you can see that Virgo had a bit lower sensitivity than the other two LIGO detectors that are quite similar. And as you can see, each detector has its own line because they depend very strictly on the specific small sensors in the detector and also on the specificities of the site. For example, the main line in the US is at 50 Hertz, while in Europe is at 60, and then you have all the harmonics around that. Okay, so okay, now the tutorial is ended. So the idea was to show you how to plot the sensitivity in a nice way with GWPy. And again, you have here some questions if you want to play with this data. Okay, and again, I think I will stop here for a moment so that I give you time to have a look and ask questions.
So we have a question from Discord from Koei. He just wants to know, just out of curiosity, what is the time resolution of this data?
So what do you mean by that? So the sampling is 16 kilohertz or 4 kilohertz, depending which data you decide to download. Internally we use 16 kilohertz, but sometimes you don't need such higher sampling rate, so it may be enough to use 4 kilohertz data. I don't know if it was, I guess that's what was your question.
Reply, thanks.
Okay, so let's go on. Before the next tutorial, I need to give you a short introduction. So, as I mentioned in the tutorial we just saw, when we look at gravitational wave data, we need to analyze both the time and frequency content of the data. And the typical way to have a look both of the time and the frequency in one plot is the spectrogram, where basically you have this bidimensional map that I will show you just in the tutorial, where every beam is a fast Fourier transform in an interval of time and frequency. But all the beam of the typical map of a spectrogram are the same. Actually, for the characteristics of our data, we found it useful to have a different representation of the dimensional representation of the data that is called Q transform. So the idea is that basically you project the data on a basis of sign Gaussian, and basically this basis you decide the length of the temporal part by the width of the sign Gaussian and the frequency by the frequency of the Gaussian. This practice allow you to have tail in this bidimensional space in which you are checking both frequency and time. But this tail, they are not necessarily of the same the same width in frequency of time, but you can have a tail that have a very defined, very specific small interval concentrated in a small interval of time, but a big interval of frequency, or vice versa. You focus very much on the frequency and you check a broad interval of time. And usually what you can do with this plotting is that you can control this behavior by a quantity that is Q, and that is defined by the central frequency divided by the delta, the central frequency divided by the delta F of your tail, that is the Q factor, the quality factor. And basically, usually what you do is that when you are analyzing low frequency data for which in the low frequency part you have this the behavior, the temporal behavior. You don't need to have very precise knowledge of the temporal behavior because it's very slow, but you need to have a very precise knowledge of the frequency. So usually when you plot this part of the data with low frequency content, you use IQ. Vice versa, when you are in the low high frequency part, in that case, you are more interested to be precise in time, so you use low Q. Okay, so this was just the disclaimer, and now I show you the tutorial. But before that, I copy the link. Okay, so this I copied in the Zoom chat the link. And now I should find my screen. Where is, yes. Okay, so this is the tutorial about the bidimensional visualization of the data and the Q transform. As usual, we need to install GWPy. And okay, you know about that. Okay. Okay, so in the first part of the tutorial, there is a bit of discussion about the spectrogram I mentioned. So there are different ways to do the spectrogram depending basically how you average, how if you are analyzing a short interval of data or a long interval of data, but this is and then after that I show you how the plot look like with the Q transform instead. So in the first part of the tutorial with the usual GOSC package, we check which is the GPS time. For example, in this case, we analyze the BNS, so GW170817, and we get the data for Livingston in an interval of 500 seconds before and after the GPS time of 170817. So with this cell, we just got the data, and with this command spectrogram 2, we plot the spectrogram, which look a bit weird because we have to set a bit of limit and make it a bit more readable. Okay, so now it looks a bit more with some colors, but you cannot really see the event. What you see is this line here, which is a glitch, because around the event there was a loud glitch. The event is basically barely visible here. And then you see a bit of the lines. This horizontal line here are the peak, the line I was mentioning we were seeing before in the ADS, in the amplitude spectral density plot. So at this point, so as you can see here, this is a standard spectrogram with every beam is a Fourier transform in the interval, and all the beams are the same. So it's not easy in this way to really see the event. It's also, you would need also to zoom a bit here. Anyway, the idea is to show you how to use the Q transform to get something from this plot. And we do that with Hanford, well, we could have done also with Livingston data, but here is done with the Hanford data in a segment, in this short segment around the GPS time of the event. And the command to just plot the Q transform is very simple, is just Q underscore transform, and this is the range in frequency that you are looking at. And again, here it's not very clear, there is not much to see. And there is not much to see because first of all, you need a bit of, it's better to have a logarithmic scale. And then the more important, the other important trick is specify which is the range of this factor Q. So as I was mentioning before, you have to decide this range in the basis of which is the part of data you want to focus. Since the BNS is a long signal that has many cycles and a very low frequency, a low frequency tail. In this case, the Q values that you need are that you are interested are quite high. So if you fix the Q range around 100, that's you see already that the signal is much clearly visible, and it's even better if you. I think here there is a zoom. Yes, if you zoom around the time of the event, here there is a bit of play with the Q range. Okay, so then the rest of the plot, I think, is the same exercise, but with Livingston data. And the point is that the problem with the Livingston data is that there is a loud glitch, as I was mentioning. This glitch that we see, this line that we see here, is the same that we saw at the beginning. This is the same thing that we saw here. And it's due to the fact that in Livingston there was a glitch superimposed to the data. So again, if you play a bit with the color and the scale of the z-axis, basically, so with the scale color here, you can distinguish again the event and the glitch. That then, if you check the paper, this was removed in the analysis. Okay, so okay, this is again the end of the tutorial. The idea here in the challenge is that you play with another event that was just a few days before this one, so 17/08/17. And the point is that while the one I showed you here, the 17/08/17 is a BNS, so it's a signal, a low signal that lasted a few seconds with many cycles, and in that case you need Q range quite high to clearly see the signal. Instead, the GW 17/08/14 was a BBH. So which means that it lasted few cycles, was just a short event. And in that case, to really see the event in a spectrogram, you have to use a much smaller Q value. Ask question and play a bit with this.
Got I have a question from my side. You showed these Q transforms. I'm just wondering, curious, is there any kind of machine learning techniques or computer vision techniques that's currently being applied to detect these events? So things like using Agata transforms to detect these kind of events.
Yes. So yes, so there is a lot of machine learning. It's the application of machine learning. It's quite recent, but there are many different tools that start from the spectrograms, the Q transform or similar things, to try to distinguish signal from the glitch. Because the point is that yes, now I showed you this nice chirp, the typical signal, but it's not, we have many, so I'll show you again my screen. So this is a typical example of a glitch, so it's a disturbance basically in the detector that can have many practical reason, very experimental reason for which it can come. It can appear in the data, but there are many of these disturbances, many of these artifacts that in the data look exactly like a signal. Here, for example, this glitch, that is a specific type of glitch that is called the blip, because because this is also a sound, no? So if you play it, the play is like blip. Exactly, so that's why this glitch is called the blip. And this, for a typical detection algorithm, could look like the last part of a signal for some event. So, for example, this kind of glitch is a disturbance that can create problem in data analysis. And machine learning algorithms are usually applied to distinguish glitch from the event. The point is that at the end, there are really many techniques that are based both on images like Q-scan spectrogram, but also on the raw data. But at the end, they are not really applied in production. So in our pipeline have many analytical way to distinguish, to identify the signal, distinguish glitch and so on. And until now we have used mainly that. But the problem is that when you increase your sensitivity, then you get increasing number of events per day. And so this at some point became unsustainable in terms of the pipeline. And that's why now it's the moment in which machine learning techniques are starting to be more appealing, and I guess we will have more and more of them applied in the next data taking. It was a longer reply, but I hope I replied to the question.
Awesome, thanks.
Okay, in the meantime, we have the time to everybody. So actually, I like a lot this application of machine learning to data analysis, and this is the other part of my research activity. So that's why we can talk forever about this. Okay, so the next tutorial I want to show you is about the generation of waveform. And again, I copied this link in the Zoom. No, where is it? Sorry. In the Zoom chat. Okay. Yes, okay. So the idea of this tutorial is to, again, yes, you use other packages that are called PyCBC and LALSUIT, that are basic, that contain all the gravitational wave theory behind, not all, but some, and allow you to get the signal waveform starting from the parameter you give as input. And the package is PyCBC, and the method is called, that we use is called the getTD waveform. And I insist on the number of the name on the method because TD means time domain. And actually, if you look a bit in the documentation, you will see that there are also, because you can imagine there are many possible models that can you use. There are models that produce the waveform in the time domain, and there are models that produce them also in the frequency domain, because for some analysis you don't need the nice wave in the time domain. It's enough to have them in the frequency domain. Okay. So
can you just post a link for this 1.4 as well, please?
I didn't copy it. No, I just copied in the chat, in the Zoom chat.
Oh, okay.
Okay, so the waveform usually comes in two polarization, H plus and H cross, and when you use this method, you have to decide an approximant. So basically, which is the model that you want to use, and you can have various parameters that you can decide. For example, in this case, we have just set the masses of the two stars, so 10 solar masses, and delta t, so the inverse of the sampling frequency. And then you usually set a lower frequency because you know that your detector will usually these interferometers don't really are useful below 20, 30 hertz. The data are too noisy, so usually it's pointless to check everything below this. So that's why the minimum is 30 here. And then, okay, so these are just plotting of the all time series and just a zoom. So these are this is the first plot of the two polarization of the wave. And okay, this is a zoom just at the end. And again, so this in this part of the tutorial, the idea is show you what happens when you change the mass, keeping the rest the same. So basically, what you, as I was, this I also said before, for events that has stars with lower mass, so like in the case of neutron star, basically what you get is that your waveform is quite long, can last few seconds. So here is the time, it lasts few seconds. But with the increasing of the masses, what you get is the waveform shorten. Of course, shorten because we fixed considering that you start to analyze from 30 Hertz, so it's shorter in our the visibility band of our detectors. So, for our for what concerns the sensitivity interval in terms of frequency that is below tens, hundreds of hertz, what you get is that events that have hundreds of solar masses they last really fraction, very short time, and then when you increase, you have a few seconds, like in the case of binaries. Another aspect that you can check is what happened with the distance. So in this case, we have three distance, 100, 500, 1000 megaparsec. And what you see that if you fix the masses, basically the shape of the signal is exactly the same. What changes there is basically a the intensity, because basically the distance, if you check the formula of the typical H cross polarization produced by gravitation, by general relativity, you see that the distance is a multiplicative factor. So the distance scale linearly what you get. Okay, and this is this is quite short. That's all. And the exercise here is to play a bit with this parameter. And for example, you can do you can check on the website which are the parameter of the GW170817, which is the BNS, the binary neutron star, and you can do the same plot. For that, you can do this exercise for few events, for example, for a BBH, for a BNS, and you will see that this effect of duration and distance and so on. Okay, so this is another thing that can be useful. So I think I have to finish in 5 minutes.
Yeah, Agata, you have 5 minutes or so. So if there's any questions from the participants, then now is the time to raise them. Otherwise, we can also take things offline. So feel free to continue responding on that channel.
Okay, in the meanwhile, I check my slides. So if there are no, since I see no question, I have just few words to say before. I had foreseen another tutorial. I don't think we have the time to see it, but I just introduced the topic. So the point is that in this binary system of black hole and or neutron stars. As I mentioned, there are different parameters that can influence the waveform that we have just seen. We have seen the effect of the distance, of the luminosity distance and the masses, but then there are many other parameters like the spins, the right tension, the inclination, so everything that depends on the position of the system and the phase and so on. So at the end, you have in total 15 parameters for if they are not if the orbit are quasi-circular. So if you assume no ellipticity, and 2 more parameters for BNS because you have to consider also the tidal effect. And the way we study this, so from the data, the way we get this parameter is via Bayesian inference. So at the end, you get a posterior probability that this parameter, this set of parameters theta, describe your data given some hypothesis on the signal. And basically what you get in this last tutorial is a way to download this posterior sample that are distribution on the various parameters that you have, and then get some confidence interval from this posterior sample. But I think it's basically I post on the chat again the last link in case you want to have a look. Where is it? And okay, let me see here if I had other tips or stuff. I wanted to say that this link that I just posted on the chat for the last tutorial is based on the first catalog, but the point, the trick is to know here that every paper writing team of each catalog has a bit of freedom to decide how to provide to the public this posterior sample. It's not well uniformed yet. So if you need a posterior sample of a specific event, my suggestion is to go to the associated page of each catalog, and usually you will find there together with the posterior sample also some small notebook to plot them, because they cannot be exactly the same from one catalog to the other. Okay, so I think that's all, because it's already 3:30. I don't think we have time to play the last tutorial. I guess you can do it, I don't know, offline, and in case you have questions, you let me know.
Yeah, I can see there's no further questions from Discord that has come in. But yeah, as I said, the Discord channel will remain open, so the question you can post your questions afterwards there as well. Agata, thank you so much. That was a very interesting tutorial. I would actually like to go play with this one after the conference a bit. Thank you so much.
Consider that in general, the Gravitational Wave Open Center, so the GWOSC team is there to help. So there are, you can go in the contact page, write email, set up an appointment in the office hour if you need help, or write me. So there are many ways of getting contact.
I have a question from Koei, so I'm going to just read that out. So he says, I have a general question. I once heard that detecting gravitational wave signals is pretty hard because the typical strain size, so the background, is much larger than a signal. But it seems from tutorial 1.3, we were able to detect the gravitational wave signal quite easily. Is it because we were analyzing what we were analyzing was a cleaned or denoised data and not the raw data?
No, wait a moment, because I lost my... In tutorial 1.3, we saw the data, but we knew which data they were. We looked at the specific frequency, and this event was quite loud, and it's a very specific case. So yes, normally the data that you get are really, really very noisy. And I pointed that you already where the event was, but looking for an event when you have so much loud noise, it's not easy at all. So this is a very specific case. I can assure you that if you just get the data, plot a random piece of time, even if you know that there are data there, it's not easy to see them or to find them.
Awesome, thanks. You can see he's typing. So let's if there's a follow-up question. He says thank you.
Okay.
Michael also says thank you so much. It was a very interesting tutorial.
Good.
Right, I think we're just over time now. So thank you so much, Agata, once again. And yeah, we look forward to many more gravitational wave detections. Thanks.
Yes. Thank you. Bye-bye.